Okay, hello.
Hi.
This is our very first calculus lesson, and I am so excited to start. I hope you are too.
Yeah.
Okay, perfect. Calculus is actually seen as a very difficult course, but it's actually not that bad once you start getting the hang of it. But let's start with the basics today. So, in calculus, before we get into the real calculus, let's talk about scalars and vectors. Now, have you heard of these before? And it's totally okay if you haven't, but we're going to get into it anyways. But if you have, we can start off with that.
Actually, not sure, but it's something about quantity and direction.
Correct. Now, scalars um, are only based off of magnitude, and this is like the quantity that you were speaking of, right?
Mm-hmm.
Now, magnitude basically means a numerical value, like a number, right?
Mm-hmm.
Um, on the other hand, vectors care about magnitude and the direction. Okay, so some examples that you've probably heard of in real life pertaining to vectors and scalars. So let's stick to vectors first. You probably have heard of acceleration,
Mm-hmm.
right? Like a car accelerating. Velocity is a vector.
Mm-hmm.
Force is a vector. Similarly, for scalars, you have speed is a scalar. Distance is a scalar. So when I say that these three are vectors and these are scalars, I mean that for vectors, the direction is usually denoted with the sign. So, for example, let's say you have a number line. Let's just keep it really basic, right? Um, you're, this is the origin, that's the zero, and this is positive two. And actually, let's just call it two here, right? So if you're starting on the number line right here, you can go 2 units to the right and you can go 2 units to the left. If you were to go 2 units to the right, you can call it positive two. So you're basically telling me or telling whoever's reading your work that right is positive, which inherently makes left negative. So if you were to go from 0 to 2 in the left direction, that would mean um, you had a displacement of -2, right? But the
Mm-hmm.
distance you traveled is 2 in both cases. So this is how displacement is a vector, but distance is a scalar, right? So even though you're traveling 2 units,
Mm-hmm.
um, where you're traveling makes a difference for vectors, but it does not for scalars. Okay, does that make sense?
Mm-hmm.
Okay, perfect. Now let's start with like a fun example scenario. Now, for example, you are looking at a racetrack, and it's a very simple racetrack. This is, let's call this right here the finish line, okay? And you have a car that is, let me draw a better car actually. You have a car that is just on the racetrack and it's going to move, right? Now, imagine there is a sensor setup right here. So this is our little sensor, okay, on the finish line. And it's basically measuring the distance that the car is away from it. So for example, right now the car is like a distance X away. And then if it were to come on the finish line, it would be a distance of 0 away from the sensor, okay? So let's delete that. Okay, now we're just gonna start with a couple scenarios. Um, and you pretty much have to tell me what the story of the the race car and the racetrack, etc. is. Okay, so let's start with a graph. This will make more sense once I actually draw the graph. So this is time in seconds, And then we have distance from finish line, okay, on the y-axis. Okay, so this is our first graph, and it looks something like this. Okay, now what does this graph tell you about the car? And you can start, like, let's start with, so we know that the sensor is actually measuring the distance from itself to the car, right? So at time t equals 0, the distance is not 0, right? It's some distance away, and we can call it distance d, okay? It's some distance d away when the sensor starts recording data,
Mhm.
right? And then what happens over time? It starts going down, and at the end, the sensor says that the distance, the distance from the finish line of the car is 0. So right here, it's 0.
Mhm.
Okay. So pretty much what's happening here is that your car starts out some distance d away, and then it goes towards the finish line. And that's this graph. That's all it's saying. Okay.
Mhm.
Does that make sense? Do you have any questions?
No.
Okay. Now, what can you tell me about how fast this car is going?
Mm, Is it d over time s? So d over s?
Yeah, so S is actually the units, and sorry about the
Okay,
confusion right here.
seconds. Oh, sorry. Uh-huh.
Yeah, no, you're good. We can call this T1
Uh-huh.
and this is T naught. Okay, so
Okay.
at T1. So yes. So pretty much what you're telling me is that it's constant velocity, right?
Correct.
Constant speed. And in this case, also velocity,
Mm-hmm.
because it's not changing directions. Now, one thing we should pretty much review a little bit is that the slope. Now, if you have a distance versus time graph, the
Mm-hmm.
slope of this graph is going to give you velocity.
Mm-hmm.
This is something that you will learn in physics if you haven't taken physics already, but the slope of a distance versus time graph gives you velocity, and that's because velocity equals change in distance over change in time. And that looks exactly like slope formula, which is change in y over change in x, except your axes have now changed to d and t, right?
Mm-hmm.
So right here you have distance, and right here you have time, and pretty much you're looking at the slope of this line, and the slope is change in d over change in t, and that is telling you the velocity, okay?
Mm-hmm.
So yeah, so the slope of these graphs is going to tell you the velocity of the car, like how fast it's moving, right? Does
Mm-hmm.
that make sense?
Yes.
Okay, perfect. Now let's look at another example, actually. Let me make these graphs a little bit smaller, and let's make a couple copies of them. Now, this is still distance from the finish line. I'm just going to abbreviate it as FL, and this is time. Okay, now the next example looks something like this. Okay. Now, what do you think the car is doing in this scenario?
Sure.
Again, you should probably just start from where you see it at the beginning.
Origin. Uh-huh.
So where is the car right here?
Oh, at the finish line.
Yes, exactly. So this is interesting because the car is actually starting out at the finish line first.
Mm-hmm.
Okay. And then what happens?
If
Eventually,
it's moving away from the finish line.
correct. It's moving away from the finish line. So technically, it starts out right here and then it goes away from the finish line like that.
Mm-hmm.
Okay. So that's pretty like weird for a car to do that if there's a race going on,
Mm-hmm.
that it's going away from the finish line and then that's when it starts out at the finish line. But these are just graphs that we're looking at. And yeah, so technically this one doesn't really make sense if there's a race. So that's also something we should note if it's actually a realistic possibility, right? Okay. So always start out looking at where it starts out and where it ends and how it gets from the beginning to the end. Okay.
Mm-hmm. Okay.
Okay. Now, okay, again, I'm gonna write out distance from the finish line, and this is time. Okay.
Okay.
Um, let's actually make a copy of this with the axes labeled.
Mm-hmm.
Okay, perfect. So this time, this graph is not linear. It goes something like this.
Okay.
Okay. Oh, again, start out by looking at where it starts. Where
Finish.
does the car start?
From the finish line only?
No, so the distance from the finish line
Oh,
at,
okay. Sorry. Uh-huh.
at this time right here, which is t equals 0,
Mm-hmm. Yeah,
it's not, this distance is not 0, so it's technically not at the finish line.
correct.
This scenario would be like this. So the car starts out somewhere here
Mm-hmm.
or some distance away from the finish line that the graph isn't labeled. So we don't really know how
Mm-hmm.
much distance, but
Mm-hmm.
it's not at the finish line for sure, right?
Correct. Uh-huh. Got it.
So it's some distance away, and then at the end, it's at the finish line, right?
Mm-hmm.
So we know that it starts out some distance away from the finish line, and then it ends up at the finish line.
Mm-hmm.
But it doesn't get there at a constant speed or velocity like the first two graphs.
Correct.
It
Mm-hmm.
does a weird curve thing, okay?
Mm-hmm.
And this is where you should start looking at the slopes, okay? How the slopes are changing. Now, we previously mentioned that slope is the velocity. The slope of these graphs is the velocity,
Mm-hmm.
okay? So that tells me that right here, the slope is something like that, right? At this point,
Mm-hmm.
right? The slope here is like that, the slope here is like that, the slope here is like that, it's like that, right?
Mm-hmm.
So technically, you're starting out with a not that steep slope, and then you end up at a really steep slope, right?
Correct. Mm-hmm.
Right? Like right there. Okay.
Mm-hmm.
So what does that tell you about how fast the car is moving?
So I think when it start, um, it was with a lower speed and gradually it's increasing its speed.
Yes, very good. Okay, perfect. And how did you come up with that? Like, what was your thought process?
The steepness of the slope is, as we can observe that as the slope is, we can see the steepened slope, and that means it is increasing in velocity.
Correct. Yes. Um, yeah, so technically the velocity would depend on your convention for the sign, but I do agree that the speed is increasing because
Mm-hmm.
your magnitude of the slope of this line is greater,
Correct.
right? So when I say what the magnitude of the slope is, that
Mm-hmm.
means how steep or how flat it is. So if it's flat, this is slope 0, right?
Yes.
And then
Mm-hmm.
this slope is slightly greater than 0,
Mm-hmm.
okay? And this is even greater, and this is like very steep. right?
Mm-hmm.
And then you could go in the other direction. You could go down. The slope here is less than zero because it's negative. But like I said, when I'm talking about speed, I care about its magnitude, right?
Yeah. Is it
Because
something related to the absolute value?
yes, exactly.
Mm-hmm.
So when I take the absolute value of anything, right, the absolute value of -5 gives me 5, and the
Mm-hmm.
absolute value of 5 also gives me 5. So what the absolute value operation rather does is that it gets rid of any sign. So you
Mm-hmm.
end up with only the magnitude of the value. You
Got
kind
it.
of, yeah, you get rid of this sign convention, okay?
Mm-hmm. Mm-hmm.
Which is why the magnitude of velocity equals speed.
Correct. Uh-huh.
Okay.
Mm-hmm.
Now, okay, let me pick up where I was at. So negative slope, right? This
Mm-hmm.
here, it's negative, but like I said, the magnitude of the velocity is still greater than zero. So even if it's not moving in whatever your positive direction is defined as,
Mm-hmm.
it's still moving at a speed that's greater than zero. And then once you start getting steeper and steeper, the magnitude increases.
Mm-hmm.
So what the car is doing in this scenario right here is that it starts out slower and then it speeds up at the
Mm-hmm.
end.
Correct.
Okay,
Mm-hmm.
perfect. Okay, now let's do another scenario. Let me get rid of all of this. Okay, our next scenario looks something like this.
Mm-hmm.
Okay, it's supposed to be a parabola. Let me actually draw that a little bit better. So maybe something like that. Okay.
Okay. Mm-hmm.
Okay, now again, what do you notice about where it starts out and where it ends?
Okay. So it is away from the finish line,
Correct. Yes.
and it's I'm not sure, but is it again going away from the finish line and then come towards finish line? Is it something like that?
Yes, that's exactly correct. So
Uh-huh.
you start out with some distance from the finish line, and
Uh-huh.
then your distance from the finish line increases
Uh-huh.
until some point, right? Because this y value right here is bigger than this y value. So
Mm-hmm.
the distance from the finish line increases, which basically means that it's going away from the finish line,
Mm-hmm.
okay? And then, like you said, the distance from the finish line is decreasing and it ends up at a distance zero from the finish line, which means it's at the finish line at the end.
Mm-hmm.
Okay, that's exactly correct. Okay, now let's talk about the speed. And also let's talk about the velocity here because that's pretty interesting. Now let me define the convention. So um let's say that the velocity is actually positive when it's going towards the finish line,
Mm-hmm.
and the velocity is negative when it's going away from the finish line. Okay?
Oh, okay.
Okay, let's define this is our convention that we're
Mm-hmm.
going off of.
Okay. So, um, if I'm observing it correctly, then I can say, okay, till the vertex of this parabola, or you can say the top point,
Yes.
the velocity is decreasing. That means negative.
Yes. Yes.
At certain point, that means at vertex, the velocity is zero, and then
Yes.
when it's changing its direction, then in short, the velocity is increasing. That means from zero, it's becoming positive, as we can see in the previous example, or you can say the as the uh, slope is steep. So that means velocity is, or you can say the speed is increasing.
Yes, but because our convention is that the positive is towards the finish line, so like
Mm-hmm.
this way, that's why this is technically positive.
Positive slope. Yeah.
Yes. Okay, perfect. That's really correct. Now let's talk about speed.
Mm-hmm.
So for speed, we don't really care about any of this.
Correct. Only quantity. So, like you can say from the start point to
Mm-hmm.
the topmost point of the graph, the speed is decreasing from, let's suppose S1 is my previous speed, so it's becoming S1 to 0.
Yes, yes, that's okay. This is important to note that this is actually zero because the slope here, if you draw a line for the slope right here, that is horizontal, right? At the very top. If you zoom in,
Mhm.
right,
Yeah,
you see a horizontal line,
correct.
right? So that's why the slope here is technically flat. So the slope is zero. Yes. Okay, keep going.
And once it becomes 0, then gradually as it's going to the finish line, the speed, or sorry, you can say the slope is increasing, or you can say the speed is increasing.
Yes. So technically, mathematically, the slope is negative,
Uh-huh.
but because we're only talking about the speed, we don't care about the sign. So it's technically becoming steeper and steeper, and therefore our speed is increasing. So yeah, correct. Okay, very good. So let's kind of play out the scenario here. So the car starts out some distance away,
Mhm.
then it goes away from the finish line and it slows down. Okay, then it comes to a stop because we're at this top point, the maximum of the graph. And then it goes towards the finish line and it speeds up. And
Hmm.
then it's at the finish line at the end. Okay,
Okay, got it.
okay, perfect. Okay, next scenario. Let's just duplicate these. Okay. Our next scenario looks something like this. Okay, and for the next three, or actually we only have two more left, but
Mhm.
tell me if this is actually realistic too. And I'm
Mhm.
going to give you both of these graphs. So one of so these are the last two graphs that we're looking at.
Mhm.
Okay. Um, what is the car doing in this first graph right here? Okay, let's start out with again
Mhm.
the top and then the bottom, right?
Mhm.
So what is going on right here at this point?
Mhm.
Ignore the
Mhm.
rest.
Distance from the finish line. Mhm. Is it?
It's
Is
some
it?
non-zero distance away, right?
Yeah.
Only at this point, it
Mm-hmm.
is some non-zero distance away from the finish line, right?
Mm-hmm.
And then what about only at this point?
The same distance. That means it's not moving.
So
Oh,
technically the
so.
distance changed, right?
Mm-hmm. Oh, yes, yes. Distance change, but in no time.
Right, yeah. So basically what this graph is saying is that starts out here and then the time doesn't change, which is why the x value doesn't change at all. This is
Oh,
technically the t-axis. This is time, right?
so
Um,
ideally, it
so,
should be undefined then.
sorry?
Is it undefined?
The slope is undefined, yes, because it's a straight vertical line.
Mm-hmm.
Um, yeah. So it's you can also say it's like infinite slope. Um, but you can also call it an undefined slope, yes.
Mm-hmm.
Basically, what this car is doing is that at some So at one time, it's right here, and then in no time at all, without time changing, it magically teleports to the finish line. So
Oh,
it's like,
got it. Uh-huh.
yeah. So it's like this, and then it magically teleports to the finish line. So like me moving the car, and technically at this time, this car is present. At this time, the car is present at all of these different locations,
Mhm.
which is not possible, at least with the knowledge that humanity currently has. Um,
Uh, yeah.
a car can't really do that, right?
Uh-huh.
Um, Now, okay, so let's look at this example, the last one, and you should do it by yourself. So just walk me through what your thought process would be on
Hmm.
how you will decode this graph.
Okay, so the car is some distance d from the finish line,
Yes, some
and
distance
as
t.
time passes, the distance is same. So can I say the car is not moving here?
Yes, correct. This is not moving. It is simply just sitting where it was at the whole time,
Mhm.
right?
Mhm.
So is this possible? Could a car do that?
Yeah, it's possible
Yeah,
if
yeah, it is.
uh, yeah.
It's just if the race has started, it doesn't make, I mean,
Mhm.
it's not a good choice to just sit there.
If it is broke down, broken car, then that.
Oh yeah, perfect. Yeah, if the car breaks down, this is how it would look like.
Mhm.
Yes. This is not moving. And why do you say it's not moving? Also, from the slope perspective.
So change in y or change in x. So there is no change in y, no displacement.
Yes,
Because
yes. Therefore, the slope,
is zero.
yes, correct. Okay, very nice.
Mhm.
Okay, now let's look at another graph. Actually, let me move this graph down. Okay. So we have another graph which looks something like this. And let's call this point A, point B, and let's call this point C. Okay. Again, we're looking at the same race car scenario. Um, and yeah, you have these 3 points,
Mhm.
and you have to tell me if the car is going faster at A, at B, or at C. Where on this graph is the car moving the fastest? Now, when I use the word moving fastest, what does that mean?
Um, in terms of,
Speed or velocity?
I think speed.
Yes, correct. It means speed.
Mhm.
Yes. Because you're just asking how fast it's going. You don't really care about
Mhm.
which direction it's going in.
Correct. Uh-huh.
Yes. Okay, so what do you think? Where
Um,
is it going the fastest?
I think at point A it's fast,
Yes.
and B, and then at C, is it zero at C?
Yeah, let's
Oh.
get to that. First, why do you think it's fastest at A?
Um, uh, if I compare the slope, it's steeper for point A, and if I consider the slope at point B, it is less steeper and is again in the, or you can say it's going opposite to finish line or away from the finish line. Am I right?
Yeah, so this line segment right here,
Uh-huh.
this is going away from the finish line, and this is going towards the finish line. But again, this has nothing to do with, like I said, the direction doesn't matter in this case, right?
Uh-huh. Okay.
So the reason that The only reason why A is the correct answer is because your rate of change along this line, and not just A, if you were to look at any point along this line, the speed is greater than any point along this line.
Correct.
Okay, and that's purely because of the slope.
Mm-hmm.
Okay, so if you were to answer a question on an exam or a test, be like
Okay.
at point A, because the magnitude of the slope at point A is greater than the magnitude of the slope at point B and C.
Mm-hmm.
Okay? Okay, cool. Now let's look at, okay, yeah. So addressing your question about point C, right?
Mm-hmm.
What is going on at point C? So for our car, this car is going towards the finish line
Mm-hmm.
and then suddenly goes away from the finish line. Like it's a sudden change because this is a corner, right?
Mm-hmm.
It's a corner. And that is actually not very realistic in real life
Mm-hmm.
because if you were changing directions, sorry, yeah, the car is right here. Yeah. If you were changing directions, so you're going towards the finish line, okay, and then you're going away from the finish line. So when you're turning, you technically make a brief stop at some point
Mm-hmm.
when you're turning like from one direction to the next, like entirely changing directions.
Correct. Mm-hmm.
So this is not realistic in real life. You can't
Mm-hmm.
technically do this. A more realistic graph
Mm-hmm.
would actually look something like, I'll need
Like
to locate it.
curve.
Yes, exactly. It would look like a curve. So something like that.
Mm-hmm.
Actually, maybe if we were to go like something like that,
Mm-hmm.
kind of reflecting this graph,
Mm-hmm.
right?
Correct.
Yeah.
Yeah.
Okay. Now, this is the last graph that we're going to look at. Let's look at something like this. I'm going to call this point A, point B, and this is point C.
Mm-hmm.
Okay. Again, at which of the points A, B, or C is the car moving the fastest? And how do you know?
I think again point A is the
Yes,
fastest.
yes,
Mm-hmm. Then
that's
point
correct.
B and then point C.
Yeah, so yes, so it's going fastest at A, then at B, and then at C, right?
Mm-hmm.
Okay, and again, just quickly, why do you think so?
Again, looking at the steepness of the slope, I think at point A, the slope is steeper than the point B, and the slope is
Hmm.
again steeper at point C. So we can say that, okay, the magnitude of slope at point A is greater than the magnitude of slope at point B and C.
Yeah, okay, yes,
Mhm.
that's correct. Perfect. Okay, and do you have any questions about any of the things we've done today? So we started out with, what scalars and vectors are. We looked at that we learned that the slope of a distance versus time graph is velocity. And then we looked at a couple race car scenarios
Uh-huh.
and also evaluated whether they were realistic or not.
It's quite clear. Only one thing I want to clarify here. So when I'm talking about the scalar quantity, I'm talking about distance, and when I'm talking about the vector quantity, it's the displacement. Am I right? So,
Yes.
so here scalar is distance, vector is displacement. Scalar is speed, so vector is velocity.
Yes, correct. Yes.
Oh, okay, got it. Yeah, just want to confirm that. Yeah,
Okay.
yeah,
Yeah, perfect.
yeah.
Yeah.
Thank you.
Okay, this was a great first class. I hope you enjoyed it,
Yeah,
and I will see you
it's
next
quite
time.
quite interesting.
Yeah.
Uh-huh.
Okay, perfect.
Yeah.
Okay, see ya. Bye.
Bye. Have a good one.